negative K. Alright, we will use that for a problem. Now, let's now talk about force on a current carrying conductor in a magnetic field. Now remember, there is always force between two magnets. A current carrying conductor is a magnet. So if you place a current carrying conductor in a magnetic field, the two magnetic fields will interact. That means if you place a conductor in a magnetic field and allow a current to flow in that conductor will move. You have any doubt about that? Well, we will have a look at that. Now here I have arranged a contraption with a magnet. This is the North Pole. Now it caught hold of my stick. That's the North Pole. I'm going to take it away. Now, if this is the North Pole, that is the South Pole. That means the direction of the field is, now look at this, it is this way. That's the direction of the field. That means if I stand here, it'll be from you towards me, North Pole to South Pole. I'm going to pass a current through this wire in this direction. What's the direction there? And I'm going to use my left hand to indicate that because we're going to work out the rule. Look at the middle finger here. That I'm going to place along the wire indicating the direction of the current. And the direction of the field will be my forefinger, which is towards me. So look at that. I'm going to, this is my left hand. The middle finger is in the direction of the current. And I need to play a little acrobatics. The middle finger is in the direction of the current. Look at my middle finger. The forefinger is in the direction of the field, and the force experienced by the conductor should then be my thumb. Now I'm going to allow the current to flow. When I connect this, when I make that connection, I want you to watch it. Now I make the connection. There you are. When I make the connection, which direction does the wire move? It moves down. Is that right? Now, if I change the direction of the current, I'm going to reverse the polarity here and see what direction the wire moves. It's moving up. Now, this time the current is this way. So, one more time, I'm going to move back the polarity so that the current flows that way. It's easy for me to show. Now, look at that rule again. Stretch the three fingers of your left hand. The middle finger, the forefinger, and the thumb, and they must be in three mutually perpendicular directions. If this is X, this is Y, this must be Z. And place the middle finger in the direction of the current, and the forefinger in the direction of the field. I think I'm going to reverse it so that it's again easier. Which direction is the current now? The current is this way. Is that right? And the field, well, the current is this way, the field is that way, and therefore, watch it again. Can you see this? The current, I'm going to allow the current to flow that way. The field is that way, then the force must be upward. Let's have a look. There you are. Force is upward. So practice that Fleming's left-hand rule for the direction of the force experienced by a current-carrying conductor in a magnetic field. What is the reason for such a force? Now here, I have a current carrying conductor. Now imagine that the conductor is coming from behind the board outside, from through the board, so that the magnetic field created by it. Now remember, we talked about the direction of the magnetic field due to a current. Now that means if your thumb indicates the direction of the current, the direction in which you wrap your fingers is the field. So look at this. If this is the conductor coming out of the board, the direction of the current, if the current goes into the board, the field is down to the right and up to the left. So this is the magnetic field due to the current in a conductor, and this is the magnetic field due to a magnet. That means this conductor is placed in this field, so these two fields will interact. Now what kind of interaction will happen? If you look at this, the direction of the field here will be from right to left. That means in this region, the field of the magnet and the field of the current are opposite. That means the two fields are almost going to cancel. How about above the wire? See, if the wire is like this, so below the wire, the two fields will cancel. And above the wire, the two fields are in the same direction. And so, what you get is the resultant like this. The field above the wire will be very intense, and the field below the wire will be very weak. And therefore, what is the interaction there? The lines of force are very close there. That means they will push against each other. So these lines of force will push the conductor from the strong field towards the weak field. And this is the mechanism of the force experienced by the conductor. In other words, it appears that the wire is being catapulted. You know how a catapult works? When you use the tension on a rubber band to throw an object, is that right? So the wire is actually catapulted from the strong field to the weak field region. That's the mechanism of the force experienced. And the direction of the force is given by Fleming's left-hand rule. I explained that to you. Now, stretch the three fingers of your left hand, the middle finger, the forefinger, and the thumb in three mutually perpendicular directions, such that, watch again, the middle finger indicates the direction of the current, the forefinger in the direction of the field, then the thumb will indicate the direction of the force. So the current, field, then that will be the force. All right. Now here you can see here the North Pole, South Pole. That means the field will be downward. The current goes that way. Can you use your fingers there? Now the field will be, let me see if I can use my left hand. Now the field is downward. The current is that way. Now look at my thumb. The thumb actually shows the force. Try and work it out on your own using your own left hand, the three fingers. Now, what are the factors on which the force on a conductor depend on? Well, if you have a conductor of length dl, now look at that, length dl inside the magnetic field, carrying a current I, and the direction of the current I makes an angle theta with the direction of the field. This is our situation. So the force experienced by a current carrying conductor depends on the current I in the conductor, the amount of current in the conductor. It depends on the length dl of the conductor inside the magnetic field. It also depends on the angle theta between what and what? Between the direction of the current and the direction of the magnetic field. Now, these are the three things on which the direction of the amount of force experienced by a current carrying conductor depend on. And I'm going to now write an equation. If dF is the force experienced by this small element of the conductor that carries a current I, and if theta is the angle between the direction of the current and the direction of the magnetic field, then dF is given by I dl b sine theta. And how do you write this using cross product? It is I dl, which is a vector. I times dl is a vector and b is a vector. It is I dl cross b. And that is the amount of force experienced by a conductor of length dl carrying a current I placed in a magnetic field B such that the angle between B and I is theta. Then the force experienced by that conductor dF equal to I dl b sine theta, which is the same as I dl cross b. And you can see that force is perpendicular to both I and B, because the cross product of two vectors is perpendicular to both the vectors. Let's do a small example. A 5 millimeter long wire segment carries a current of 2 ampere in the x direction. It is placed in a magnetic field of 0.35 Tesla in the xy plane at an angle of 45 degrees. Calculate the magnetic force experienced by the wire segment. It's a direct problem. You are given all the quantities that you need. Just pick the quantities. Our equation is dF equal to I dl b sine theta. Do we have all these quantities? We have I as 2 ampere, dl, the length of the conductor is 5 millimeter, write that in meters. And do we have B? Yes, we have. It will be 0.35. And the angle is 45 degrees. And therefore that force is 0.0025 Newton. A very simple problem. So, since the current I and the magnetic field B are both in the xy plane, what will be the direction of this force? dF will be in the positive z direction. So in a problem like this, it is not enough to calculate the magnitude. You also have to obtain the direction, because that force is a vector. And therefore, the final answer is dF is 0.0025 Newton K. The force is in the positive z direction. Let's do another one. A little more involved.